Hello everyone, we are Team 2, and today we're going to give our fourth presentation on the Cadet Chapel. Before starting, we'll be discussing the revised plan for our presentation. We have decided that to gain and convey a better understanding of the story behind the construction process, we need to follow the actual sequence in which the construction was carried out. Consequently, our project will be divided into four distinct phases: the design phase, groundwork phase, structural phase, and renovation phase. Each of us will take the role of a manager for each phase. Although there are areas that could be improved, we will not go into the supplementary explanations about the design phase due to time constraints. We will continue the discussion on trusses, folding, and flying buttresses during the structure construction phase. Moving on to today's focus, let's step into the groundwork phase. From this moment, we are the managers responsible for the foundation of the USAFA construction in Colorado Springs. Let's prepare to build what will be the pinnacle of the Air Force education facilities in the United States. Geography. Following numerous surveys and engineering studies, the Secretary announced the selection of an 18,471-acre site north of Colorado Springs in June 1954. They found a huge amount of land to construct their Air Force Academy, but it doesn't mean that buildings can be built there immediately. Based on the geologic studies, the groundwork that is the basis of the construction should be carried out first. That's what we're going to do from now on. Let's take a look at the geography. The USAFA, positioned about 11 miles north of Colorado Springs, Colorado, includes 28 square miles of the Great Plains east of the Rampart Range, which is part of the Rocky Mountains. There are various geographical and historical sites, but the key lies in the formation of the Rocky Mountains, located in the west of the Academy area. In the process of forming Rocky Mountains, a geological formulation called Dawson Arkose was formed by mixing alluvial fan and fluvial deposits, and this Dawson Arkose is the predominant bedrock of the area. Now, we have a rough idea of the geology of the site. With this base knowledge, we have to start field investigations of foundation conditions. The purpose of the preliminary investigation is to determine the distribution of the sand and gravel cap on mesa, and to derive enough information about their thickness and physical properties to determine whether the land is suitable as a foundation for heavy structures, such as the Cadet Chapel. The first boring test on the mesa consisted of 20 to 30 inches small diameter holes. Cuttings from these holes gave some information about the Douglas Mesa gravel, but differentiation of the pediment gravel from the underlying arkose was often difficult. Many were stopped by boulders, and only a very few entered recognizable Dawson Arkose. After the first test, SOM determined the location of the building more exactly, which means we could enlarge the boring test. More than 60 holes, 45 centimeters or 60 centimeters in diameter, were drilled to investigate the areas. The large diameter auger could remove or pass by most of the smaller boulders, so some holes could be reached to the Dawson Arkose. 3 of the 60 holes reached Dawson Arkose and succeeded in getting information about it, but it still seemed a bit lacking. So 8 test pits were dug at various points on the mesa, and some of them are up to 7 meters deep. The pits exposed enough of the pediment gravel to show the approximate proportion and distribution of the larger boulders, and some pits exposed Dawson Arkose. Final field analysis. Many tests have been conducted based on soil testing. First of all, the longitudinal section of the pit was investigated to find out the slope of the building site. As the pit was located at the center line of the building site, from 7,220 feet to 7,130 feet east on the western edge, it could be seen that the slope was about 10% eastward. Also, size analysis of soil gave information about the different sizes of stone and soil which help determine the location of the project, whether it's a suitable for a specific construction activity or structure, and also determine the type, size, and depth of the foundation. The test called SPT, short for Standard Penetration Test, was held. It could be useful for testing support as a foundation of soil, increasing the accuracy of the foundation design and the safety and stability of the structure. And lastly, plate bearing test made it possible for evaluating soil subsistence and stability under load, which led to predict soil performance, avoid excessive foundation design, and reduce construction costs. One of the tests gave information on the frictional angle and cohesion to the gravel. Samples taken from soils having a penetration resistance of 32 to 42 blows per foot and a dry field density of 106 to 117 pounds per cubic foot had angles of internal friction ranging from 35 degrees to 44.2 degrees and cohesion ranging from 0.1 to 0.7 ton per square foot. In addition, large pebbles ranging from several feet in diameter at various depths were found below, showing that they generally become denser towards the bottom. This information showed that the gravelly area could support heavy structures, especially deeper down, where it got stronger. Conclusion: based on these various tests, we can make some decisions. First, it turned out that the ground is proper for deeper foundation using drilled shafts, with no very serious engineering geologic problems. Deeper foundation has some advantages. It's cheaper and quicker than digging out large areas, and this method is faster and uses simpler equipment. So such advantages make it a good choice for building strong foundations. Second, it was decided to look more into deep foundations, like those used for big piers or bridges, by doing full-scale tests such as the Caisson load tests to see how well they hold up under heavy weights. Now, this approach was chosen because it seemed to be the best balance of cost, strength, and speed for construction. Third, the need for retaining walls to prevent soil from being pushed to the construction site had also emerged in order to build on a terrain with a 10% slope, and the above result values, especially the friction angle, were used as an important design factor in the design of the retaining wall. We have completed investigating the survey of the environment and foundation within the site through soil inspection, and as a result of various tests on these, we have found that the retaining wall and Caisson method were the key to talk about in the next time for future groundwork processes. We will explain how the retaining wall was designed and the Caisson processes, along with the drawings and example models handed over to the architect. Thank you for listening.